This is the second of two videos about kinetic molecular theory. In the first video, we talked qualitatively about how molecules move on a microscopic scale, and now we're going to talk a little bit more quantitatively about how fast they move and about how we measure those values. So we're going to talk about molecular velocity. So we just finished doing a qualitative view with the assumptions of our theory. Now we're going to do quantitative with math. We're going to use something called the Maxwell-Boltzmann distribution, named after two scientists who were experts in gas statistics who studied this. So the Maxwell-Boltzmann distribution is going to be a plot of the number of molecules of a gas that have a particular velocity, which we represent with the symbol mu. Looks like a U with a left-hand tail. So let's think about what we expect the distribution to look like. When we take the temperature of a gas mixture, we're taking an average measurement of what the average speed of all of those millions of particles look like. But in reality, not every particle has the exact same velocity. There's a distribution. So the distribution is going to look like this. So it looks roughly like a bell curve, but it has a few differences. So here, this curve is tallest in the middle. And in this case, being tall means the Y value, which is the number of molecules, is high. So there are many molecules with this speed in the middle. So lots of molecules with like an intermediate speed. And the other interesting part is the tail right here. So rather than a normal bell curve where the left tail and the right tail were the same length, in the Maxwell-Boltzmann distribution, this right-hand tail is a bit longer than the other side. So there's a long, flat tail at the end. And if the value is very flat, that means the number of molecules here is very low. So there are few molecules in our container that have this high speed. So when we take the temperature, we're taking an average. We're taking a snapshot of all the molecules inside the container. And so if we wanted to take a snapshot and pick a value to represent this entire curve, which value would we pick? So I'm guessing most of you would guess on your first try that if we wanted to pick one value to represent the curve, we would pick the maximum, the very highest value, right here. And so that value is called mu sub p, or the most probable speed. So if we magically had the ability to measure the velocity of a particular particle that we snatched out of the container and put it on a little treadmill and figure out how fast it was going, it's most likely that we would pick a particle with this speed, because there are the most number of molecules here. But that's not the most accurate representation that we could pick, because remember, the tails are not the same side. This tail on the right side is much longer, so there's a few more particles on this side at higher speed than there are on this side at lower speed. So a better representation of the average speed is going to be right here, slightly higher than that most probable spot. So we're going to call this value mu RMS. And that stands for the root mean square speed. And this is the value we're going to use for our average speed. This one right here, that's the one we like. So this root mean square speed, slightly higher than the most probable speed, is going to be the snapshot we take to represent how fast, on average, the molecules in this container are moving. And this is an excellent graph, and excellent graphs are always accompanied by excellent math. And so we're going to borrow some formulas for kinetic energy from physics, our buddies in physics. So one formula that you may have seen if you've taken physics before is kinetic energy is 1/2 mv squared. We're just going to adjust that formula a little bit to better fit our gas molecule model. So instead of mass, we're going to use molar mass. And instead of velocity, we're going to use specifically that root mean square speed. So kinetic energy is the molar mass times 1/2 times the root mean square speed squared. And a note about kinetic energy, since this is our first time doing math with it, the units for kinetic energy are going to be joules, which is kilogram meter squared per second squared. So the units are going to be a little bit different for this one. And one thing that's super cool about kinetic energy is the same for any gas at the same temperature. So we'll talk about this more on the next page. But what this means is that no matter what gas you're looking at, if it's helium, if it's neon, if it's argon, if it's carbon dioxide or oxygen or a mixture of them, if they're at the same temperature, the snapshot, that kinetic energy is going to be the same for the mixture. All right, so this is one way of relating kinetic energy to that root mean square speed, but we also know from our assumptions about a kinetic molecular theory about number 5, that kinetic energy is also proportional to the temperature. That if we increase the temperature, those particles are going to be moving more quickly. And we have a formula to help us represent that as well. Kinetic energy is equal to 3/2 times our gas constant R times temperature T. This is our gas constant that we've seen before, but when we use it in this formula, because we want to get a unit of joules for the answer, we need to use a different form of R that has joules in it. We're going to use the 8.314 joules per mole Kelvin form of this. So, especially with these kinetic energy formulas with the root mean square speed, make sure you check your units because they can vary and you want to make sure that they cancel out. Okay, so now we have kinetic energy and it's related to 2 different equations. So we can set those equations equal to each other to find a relation or to find a formula to express the root mean square speed. So if we move those variables around, we can get 3 times gas constant times temperature over molar mass and the square root of that. So we won't be doing a lot of calculations with this, but this is going to give us some interesting information about the relationship of these variables. So we really care a lot about the velocity of these particles, and in this formula we can see that velocity is proportional to temperature and to 1 over the molar mass. So we're going to take a closer look to see what that distribution that we drew in the first picture would look like if we change the temperature or if we change the identity, the molar mass of the compound, and look at how that shape changes a little bit. So here's that formula again. At the top, root mean square speed, square root of 3 RT over molar mass. So let's look at each of these variables and see how they affect the root mean square speed shape of that Maxwell distribution. So let's look at temperature first. So according to that formula, root mean square speed is proportional to the square root of temperature. So they're directly proportional. That means if you increase one of them, it's going to increase the other one. So that means that if we have a gas at high temperature, that those molecules are going to be moving faster on average. We know that in every gas mixture, there are going to be some very slow particles and some very fast particles, but on average, a snapshot of that gas would show faster moving particles. So let's look at a few different temperatures and see if we can predict what that shape might look like. So we'll have number of particles against the velocity, and we're going to vary the temperature. So let's pick a gas and stick with it. So let's say we're looking at helium. So here's our line that we drew on the last page, very tall, very thin, and with a particularly long tail on the right side. Let's say that was measured for helium at 100 Kelvin. So now what would this plot look like if we were to increase the temperature? We know that increasing the temperature should increase the root mean square speed, and that the root mean square speed was slightly to the right of the most probable speed, but we're not simply going to take this graph and shift it over to a higher velocity, because that's not what actually happens. What happens is more of a flattening of the curve, because even as we increase the average temperature of the mixture, we're still going to have particles back here that are moving very slowly, as well as particles on average moving here a little faster, and a few particles moving very, very fast. So as we shift the root mean square speed to the right, we're also going to be decreasing the height. We're going to be smushing it a little bit. So here's a slightly smushed hump with a very long tail at the right. We'll say that's at like 500 Kelvin. And if we keep going, we're going to continue with the same trend. So as we shift the root mean square speed over, the curve is going to become flatter and flatter. So it's going to be very long and very flat for 1000 Kelvin. And if we look at the root mean square speed, which is slightly higher than the highest point, we would say it's right about here. Root mean square speed, probably right about here. Root mean square speed, and right about here. So if we look at the position of those points, the root mean square speed is increasing. Even though the number of molecules at that speed is less, the value of the speed is increasing every time we increase the temperature. So those two are directly proportional. So we've talked about temperature. Now let's look at molar mass, the other interesting variable. So the root mean square speed is proportional to 1 over the square root of molar mass. So these are indirectly proportional. So that means if we increase the molar mass, if we have heavy gas molecules, that the speed is going to do the opposite. So these are going to move slower on average. It's like trying to move an elephant. Elephants are much bigger than people, so on average, they move slower. They can still run just as fast as a person, but on average, they move more slowly. If we were to take a snapshot of a herd of elephants versus a herd of people, the elephants would be moving slightly more slowly. So let's look at a couple more distributions of velocity. And let's look at distributions and change the molar mass, but keep the temperature the same. So let's pick a temperature. Let's pick 1000 K. So we're thinking about how the shape changes. So we have some of these very tall, thin shapes at low velocity, and we have some of these very wide, flat shapes at higher velocity. So which one of these shapes is going to match a very light gas. So if we have a very light gas, would you think that the particles would be moving more quickly or more slowly? Is it more like the person or the elephant? So if you have a light gas molecule, it's going to be moving more quickly. So it's going to be more at higher velocity. So it's going to look like this wide one that we drew up here. Very low and very wide. So that could be for helium, a very lightweight gas. If we pick something slightly heavier, like neon, neon is going to be moving on average slightly slower than helium. So it'll be a little bit taller, it'll peak a little bit earlier, and it'll be a little bit shorter. So that could be for neon. And if we were to pick something really heavy, like argon gas is like a herd of elephants. On average, the herd is going to be moving much slower than something that's much smaller. So we're going to have a very tall, thin distribution at lower velocities for argon. And so you'll probably notice that when we made a series of different distributions at different temperatures for the same gas, and when we made the distributions for different gases at the same temperature, the plots look very much the same. We just need to keep in mind which direction the relationship goes. So for temperature, as we increase the temperature, the distribution becomes more flat and moves towards higher velocity. When we change the molar mass, as we go to a heavier molar mass, we're becoming more thin and tall at a lower velocity. So this gives us a lot of information about how to make predictions about the average snapshot, about that average kinetic energy of a component. So we can see, as we said, even though kinetic energy at a particular temperature is the same, no matter what the gas is, if it's at 100 Kelvin, the kinetic energy is the same. The root mean square speed is not always the same. If you have a lighter component, you are going to end up with faster moving particles that give that same kinetic energy at that temperature. So these are important relationships that we should be able to discuss. And that is the end of the video on kinetic molecular theory.